In this video, we're going to dive into how Farcaster's diff sync works. So the problem is that any two hubs, like Alice and Bob's hub, might get out of sync and have different sets of messages. There are many reasons why this can happen. Gossip could just have failed at propagating some messages, Bob's hub could have gone offline for maintenance or other issues, and ends up with just a very different set of messages. So Gossip will never catch this up, right? It's only going to send new messages out. And so Bob needs a way to heal all these old missing messages. And a simple protocol might look like Bob's hub at periodic intervals just picking a random peer, let's say Alice in this case, and saying, hey, give me a list of all your messages, and checks it against its own messages and just saves the one that are different. Or if you wanted to be more efficient, maybe it asks Alice for a list of message IDs, compares it against its own message IDs, and then only gets the actual messages that it's missing. This naive algorithm works in the base case, but when you have 1,000 hubs with 100 million messages, it can actually get very, very slow. So the way Farcaster's diff sync work is it uses a data structure that's known as a time-ordered prefix trie. So the first thing it does is it takes message IDs and puts them into a trie. So the idea here is that we would have, let's say the messages were A111, A112, we would insert them into the trie where this node is A111, and this stores A112. So this trie very efficiently tells you that both these messages exist, but shares the bytes for the first parts of the message and only stores the diffs, so the amount of space used is very, very low. The second thing that this trie stores is at each level, the value can store the count of how many messages it has and the hash of all of those messages. So you very efficiently know that, hey, under the A node, all messages starting with A, I have at least 10,000 messages or 581 messages or whatever. And so it's very easy for two different tries to compare each other and say, I don't have to walk through this whole list. I already know that there's a bunch of stuff that's shared here. We're going to make some further optimizations. So the first thing that we're going to do is actually going to introduce timestamps. So rather than just put the message IDs into the trie, we're going to prefix them with the timestamp of the message and then put them into the trie. This makes each message a little bit longer, but gives us the nice property that the tree is sorted by time, with oldest messages coming here and newest messages coming here, which actually gives us a really nice property that we can use in sync next. Now, in this example, we use 2 bytes that are in blue to store the timestamp and 2 bytes to store the message ID, but in reality, there's actually 36 bytes, and so it's a much, much longer and deeper tree. So let's talk about the algorithm itself. So we use this algorithm called comparing exclusion sets. And so what an exclusion set is, we'll walk through how to create one, is let's say you have this trie. And this is simplified. It uses human readable names here to make it easy to understand how it works. And the basic concept is that in 2022 January, there were 3 messages produced with an ID of 1, 2, and 3. So to figure out the exclusion set, you take each node of the most recent message. So this is the most recent message. And then you find all of its siblings, and you calculate the hash of the siblings. So in this case, 2022 is your latest. You'll go to the node 2021, which is its only sibling, and you'll take a hash of its value. Next, you'll go to January. You'll find its siblings, which are none. So ignore the green here, that's a mistake. There's actually no siblings, so we'll take a hash of 0. And then we'll go to 3. And in this case, we have a hash of 1 plus 2. So we'll combine both of these and take a hash of this value, and that's the third value. So for each level of the tree, you will have one hash value. So hash of 2021, hash of 0, hash of 1 plus 2, which is the exclusion set value. And when hubs communicate, they'll actually swap exclusion sets. So you can imagine that even for a tree that stores 60 million messages, there's only about 26 or 36 or so hashes that get swapped for each level. And then hubs do the diff syncing using this. So here's an example we've set up where there's hub A and hub B, and the only thing that's different is hub B has an extra message 12 in its March node. So hub A calculates its exclusion set, which is hash of 2022, hash of February, and then hash of 10. And hub B does the same. So hash of 2022, hash of February, which is the sibling of March, and hash of 10 plus 11. And so when they compare these 3 values of these 3 levels, they notice that the hash of 10 plus 11 doesn't match the hash of 10, which means that at this layer, there's a bunch of stuff that's divergent. And so now hubs can use a more traditional diffing algorithm to figure out all the gaps here. So this is how diff sync works and enables us to quickly eliminate large sections of the tree, so we can use a more traditional algorithm to focus on the specific parts of the tree where changes are happening.